So I'd like to thank the organizers for the invitation and the opportunity to give this talk. It's always nice to be in India. I shall mention that this talk is based on joint works with Vyjayanthi, Chari, and Raghavan. So yeah, I'm going to talk about imaginary modules and how they come from looking at tensor product of snake modules. So let me start off by saying some words about the origin of this imaginary, the notion of this imaginary representation. And this goes back by the work of Bernard Leclerc on a conjecture of Bernstein's and Levinsky about the multiplicative structure of the dual canonical basis, where they conjecture that if I take two basic elements, they Q commute if and only if the product is again a basic element up to some particular scalar. So in particular, the conjecture would imply that for any basic element, its square is again a basic element up to a particular coefficient, right? And what Leclerc did is he constructed basic elements B, where this implication failed to hold. And he did that, and he called such elements imaginary elements for the dual canonical basis. And he constructed such elements for types A5, B3, C3, D4, and D2. Therefore, using natural embeddings, he was able to prove that such imaginary elements would exist in all types except A1, A2, A3, A4, and B2. Okay, so how do we go from this to representation theory? There's a strong connection between, type A at least, okay? There's a strong connection between the dual canonical basis and simple representations for the affine Hecke algebra in a way that when you take a basic element, you can associate a simple module for the affine Hecke algebra. And moreover, the product of these two basic elements encode the induction product of these two simple modules. Okay, so, but for this talk, I'm interested in representations for the quantum affine algebras. So to go from affine Hecke algebras to the quantum affine algebra, there is this Schur-Weyl duality functor, which goes from the representation theory of affine Hecke algebras to the quantum affine algebras. And as long as you are careful with the rank of this quantum affine algebra, this sends irreducible modules to irreducible modules and preserves this induction product and sends it to tensor products. Therefore, by constructing these imaginary elements for the dual canonical basis, Bernard Leclerc was able to produce modules such that the induction product, simple modules such that the induction product was not simple. And therefore, using this Schur-Weyl duality and being a little bit careful with the rank, he was also able to produce simple modules for the quantum affine algebra such that the tensor square is not simple. And that's what they call imaginary representations. Okay, and all these machineries, being careful with ranks, etc. So the smallest example he had of imaginary elements in type A5, he was able to construct an imaginary representation in type A4 for the quantum affine algebra. So this is the definition essentially. I mean, I could have started with that, but why not? And okay, and this is a bit surprising because in this theory, and from now on, essentially every time I mean representation, without further any comment, I would be essentially meaning representations, finite dimension representations for the quantum affine algebra. Okay? And generically, when you take two such irreducible objects, it's again irreducible. So the fact that this tensor square is reducible is a bit surprising. In particular, when you take such irreducible module and you tensor square it with itself, and this is again simple, we call it real. We've seen this definition before with David's lectures last week. And until fairly recently, not many examples of imaginary modules were known. So this work of Leclerc, for instance, is from 2003. And only later on in 2018, Lapide and Minguez, they worked in a similar problem. However, now for complex smooth representations for the p-adic GLN. And they gave, and there the simple modules are parameterized by what's so-called the Zelevinsky multisegments. So imposing some restriction, some regular restrictions on this smooth segment, they were able to classify a representation there, if it's either real or imaginary, using their own language for that. Okay. So, but this is again for the pedigree groups. There's a strong connection again from representations of the pedigree groups with the affine Hecke algebras, and then again we can use Schrawan duality to obtain representations for the quantum affine algebra, which are imaginary under their work. But this is far from exhaustive because they are limited to this regular mood segments. And this is also limited to type AN. Other types, they're not able to cover this, at least now. And what I want to do in this talk is to give a direct construction of an infinite family of imaginary modules for the quantum affine algebra. And which we do not use all these dualities and so forth, right? So it makes a little bit sense. And what we get is that such modules, they occur as subquotients of tensor products of prime and real modules. And moreover, these prime and real modules are in fact reachable in the sense of cluster algebras. So they should correspond to cluster variables in that sense. So there is also another layer of interest here, which comes from this connection with cluster algebras. I mean, this was extensively talked by Davi Hernandez last week, for those who are here. I'll just give a brief summary of the main result, which goes by, it's to Hernandez Leclerc, Fenching, and Kashwarak in Park. What they proved is that inside the category of finite dimensional representations for the quantum affine algebra, there is a skeleton subcategory, which is a monoidal categorification of a cluster algebra, meaning that the Grothendieck ring of this particular subcategory is isomorphic to a cluster algebra in a way that sends cluster variables to prime and real simple objects and send cluster monomials to real simple objects. Okay, so this is nice. We have this machinery, this beautiful connection. And even though we are not able to classify simple prime and real representations in terms of the Drinfeld polynomials, we have this machinery, right? So of the cluster that we can start mutating things and get new prime and real modules, and therefore have we can take tensor products of them. In the same cluster, they remain simple, so you have lots of simple modules, example of simple modules in this way. However, imaginary modules cannot be obtained in such a way. So in this context, what we're doing here, comparing with the previous slide, is we are obtaining certain cluster variables such that the product is not in the span of the cluster monomials. Okay, so what would be a basic and naive approach to prove that any representation is imaginary? So, I mean, as was extensively mentioned here, simple modules were parameterized by Drinfeld polynomials by Chari and Presley. Now you know what Drinfeld polynomials are, so I'm calling them pi, and for each pi you have a finite dimensional representation associated to that, which I will call V pi. The quantum affine algebra is a Hopf algebra, so we can take tensor products, so this is well defined as a representation. And when you take the tensor product of two simples like that, the product of this Drinfeld polynomials is again a Drinfeld polynomials in the Drinfeld polynomial, and moreover, this simple module is always a simple factor of this tensor product. So we know that always holds. And there's a refined notion of weight space that I'm going to come back to that later. So it would suffice to find some particular weight where the dimension of this weight space in the tensor product is bigger, strictly bigger than the dimension of this weight space in the associated irreducible. So this is the most naive way you could think of. But, well, this is difficult in general, right? Otherwise, my talk would be over. So what we do instead. So this construction was proposed in work with Chari, and we use the following approach. So basically, I'll give you a recipe that we hope to follow it. I start off with two simple modules V and W, and I just request that one of them is real. Okay, by a result of Kane, Keshwara, Keen, and O, we have that the tensor product V, the tensor product V and W has simple SOCO and simple head, and moreover, the head of W tensor V is isomorphic to the SOCO of V tensor W. Okay. So we have plenty of real modules, so it's not hard to find one of them, and then we have this essentially for free. Now what I'm going to consider is this fourfold tensor product, and taking the identity map at the ends and this canonical projection of V tensor W onto its head, we have a surjection from this fourfold tensor product to this module. Okay, this is all canonical. Now I start with imposing my conditions. The first conditions is there exists a submodule M1 inside the tensor product V tensor W of length 2. Right? Well, since V tensor W has simple SOCO, the SOCO has to be a submodule of M1. These have been having length 2. It implies that M1 mod M0 has to be simple. Simples are parameterized by Drinfeld polynomials, and that's what I'm calling pi1, the associated Drinfeld polynomial. Second condition is the image of M1 tensor M1 sits inside this fourfold tensor product has to be non-zero in the target. If that happens, it means that this is a module. Since it's a module, it must have an irreducible quotient. Irreducibles, again, are parameterized by Drinfeld polynomials, so we have a non-zero map like this. And my request is that the Drinfeld polynomial associated to this quotient is not pi1 squared. The same pi1 that I have in here. Okay? And the final and third condition is eventually what I want to do is I want to factor, so at the end we have this M1 tensor M1, we have a composite map all the way to V omega, which is non-zero. I want to factor this map through the V pi1 tensor V pi1. And what's the quotient I have to take here is exactly this submodule. So I'm just requiring that the image of this composite map for this submodule is 0. If all these conditions are satisfied, using that this omega is not pi1 squared, we get a non-zero map from V pi1 tensor V pi1 to some other irreducible component, proving that V pi1 is imaginary. Okay, so this is the blueprint. It doesn't seem much easier than the previous slide, but the point is, if you carefully choose V and W, you have a lot of restrictions and like you could have nice properties to better understand this whole recipe. And that's what I am for in this talk. My goal is going to be able to select V and W, good modules, whatever good means, we'll get there, in a way that we can follow this recipe and get imaginary modules from it. Okay, now that my rather long introduction is over, I can plan the talk, and I'm going to use a lot of information from the previous talk, so I will just essentially fix notations from the finite algebra, from the quantum finite algebra and the representation theory. A quick review on the snake modules, which are going to be the main players of this game. A motivation coming from the extended T systems. I'll get back to that in a second. And main results and remarks. As mentioned before, G, just simple finite-dimensional complex Lie algebra of rank n, and we have LG being the loop algebra, just answering by the G by the Luhmann polynomials, and then we have a Lie structure on this vector space. And the quantum affine algebra associated to G is a deformation of the universal enveloping algebra of this LG by this parameter Q, which is a non-zero complex number and not a root of unit. Well, Sachin told us a lot, but for me, all is necessary for this talk is to know that this algebra is a Hopf algebra generated by infinite many elements, xi and phi i's, s's, subject to quite complicated relations, which are completely irrelevant for this talk. And it makes sense to consider particular subalgebras generated by this set of generators. when you take the UQ naught generated by those phi's, it's a commutative algebra, and we have a triangular decomposition. Okay? So you just have to remember the triangular decomposition for the next slide, and then you can forget it. As for the category, so FQ is going to denote the category of finite dimensional representations of this quantum affine algebra of type 1. If you don't know what type 1 means, don't worry, it's just a technical issue. For those who do know, you know. Using the fact that this algebra is commutative, fixing a finite dimensional representation for the quantum affine algebra, it makes sense to consider simultaneous generalized eigenvectors for this action. And the associated eigenvalues are what we call L-weights. Okay? So therefore, we have notions of L-weight vectors, L-weight spaces, L-weight modules, and so forth. And since we have a triangular decomposition, it also makes sense to consider L highest weight vectors, L highest weight modules, and so on. I'm not going to properly define, but it all comes naturally. Okay, what I need now is an index set for these L weights, at least for this, when we work inside the category of finite dimensional representations. And this is due Frank-Reshetikhin. And I'll just define P to be this Fourier abelian multiplicative group on the variables YKA on this range. Remember, N is the rank of the algebra. And those are going to play the game of the fundamental weights for this context. Inside this group, we can consider the submonoid generated by the same generators. And for this talk, and for the sake of the talk, I'll identify this set as the set of Drinfeld polynomials. Okay? So for each element of P plus, I have omega, I have V omega being this irreducible finite dimensional representation. And there's a canonical way for each element of P to be seen as an element of the dual of this commutative algebra in a way that you can produce your generalized eigenspaces. Okay. So it's convenient to define the set of L weights of V just looking by the elements of P such that the corresponding L weight space is non-zero. And finally, Frank and Reshetikhin, they also proved that there exists an injective homomorphism from the Grothendieck ring of this category to the group ring ZP, which is essentially defined by collecting the dimension of each L-weight spaces and put it in the position, the associated position in this group ring. Okay, so what I said up to this point is totally generic. Now I want to focus on type A, and I want to give a different notation for the set of Drinfeld polynomials because it's easier and more likable, I think. So it helps a lot. And the parameterization I want to propose now is essentially motivated by Zelevinsky multisegments. For that, we need to do some work. We can restrict to this Hernandez-Leclerc monoidal subcategory FZ he mentioned about in his lectures, where the constituents, the simple constituents are of the form V pi, where pi belongs to specifically this submonoid. So I have a lot of control over the spectral parameters that show up. So they have to be integer powers of Q, and I have some parity condition with respect to the index. Okay, so, and this is enough for everything interesting you could understand about this category, the whole category. This is enough. In is the collection of integers, ij, satisfying this property, having length at most n plus 1. And I want to define the free abelian monoid generated by formal variables omega ij, where ij is an interval here, but satisfying some strict inequalities there. So 1 less than or equal to j minus 1 less or equal to n. And it would be convenient to understand omega ii and omega I plus n plus 1 being the identity of this monoid. So given any R tuple in this set IN, I can produce an element omega S inside this monoid just by collecting its interval, its associated generator. And there's an isomorphism between IN plus and the PZ plus as defined in a way that I take this formal variable omega ij and send it to the formal variable y, j minus I, q to the I plus j. So all the parities are respected and we get this isomorphism. So essentially our index set for Dirichlet polynomials now is given by IN plus instead of PZ plus. And I'm going to work with that. So why is that helpful? Having these intervals helps a lot to understand, for instance, the reducibility conditions of fundamental representations, given as follows. So we say that two intervals in that set, they overlap if one of those conditions is satisfied. It's just literally an overlap. They have intersection, non-zero intersection. And we say that they are connected if they overlap. And when I swap the j's, for instance, the two intervals I produce, they continue to be elements of IN. So this means basically that in this case, when I take J2 minus I1, this is less than or equal to n plus 1. Okay, so we get this condition in terms of representation theory as follows. This tensor product of two fundamental representations is reducible if and only if this pair is connected. Okay, and moreover, when you look at the Grothendieck ring, what you get is this identity. And since I1J2 and I2J1, they can never be connected, this corresponds to a class of a simple module. So we get that this tensor product, the associated tensor product has length 2, and this is a complete decomposition of that. Yes, in some sense, yes. For example, when I look at this pair 0, 2, 2, 4, this is an overlapping pair because the intersection is 2. However, you have to be careful here in which algebra you're trying to understand this. So this remains connected for n bigger than 2 because we have to do 4 minus 0 equals 4, has to be less than or equal to n plus 1. And this is okay here. But when you look at this module for SL3, this is irreducible because this pair is not connected there. Okay, so I want to introduce now the main players of the talk, which are the snake modules. They were introduced by Mook and Young in 2012 for types A and B. Maybe Katsuyuki next talk will say something more for other types, I don't know. But originally they were introduced only for types A and B. Again, I'll focus only on type A. And in that language, they simply correspond to modules V omega S, where S is a collection of intervals satisfying this property. So I just have to impose that the I's are strictly increasing and the J's are strictly increasing, and that's all. Okay. They generalized this, the so-called Kirlover-Shtikin modules, which again, in this language, they can be seen as snakes, satisfying this particular property. So we start with some interval and you add one in each position and continue like that as you want. They're simply expressed in terms of these intervals, which is nice. And I mean, there are analogs of snake modules in other worlds. For instance, in the representation theory of Yangians, they correspond to skew-Yang diagrams. For smooth representations of the Pedzic geoland, they are known as ladder representations. And they all have been studied somehow independently up to very recently. And they all have this main role in the theory, essentially. Just one final definition for the snakes. We say that the snake S is connected if each consecutive pair is connected. Right? So this always holds. So what I'm imposing is basically this JS has to be greater or equal to this IS plus 1, the next one. Okay, so what makes snake modules special? well, they are special, but this is a different kind of special. Special in the sense meaning that they have only one dominant weight. So I have the set of L weights. It's always a subset of that group P. Only one of the atom elements is in fact belongs to the monoid. They are thin, meaning that each L weight space has dimension at most one. And also in type A, at least, they completely classify the family of thin modules there. Their Q character is given by a completely given by a combinatorial description using non-overlap paths. We have a complete description of primeness there, so I don't think I mentioned that, but prime module is simply a module that cannot be written as a tensor product of two non-trivial modules. So a snake module is prime if and only if the associated snake is connected. They satisfy this extended T-systems, which I'm going to be a bit more specific in a second. And finally, more recently, they proved that prime snake modules are reachable in the sense of cluster algebras. This is one, Lu. And since they are reachable, they are real. They were able to prove. You can prove independently, but this implies this. So actually, during this work, we use essentially all properties coming from the snake modules, but I'll essentially focus on these two. Okay, so let me try to approach this extended T-systems, which is somehow the motivation for part of our work. Given two snakes, S and S prime, of same length, I'm going to say that S covers S prime if when I look at each respective position of the intervals, I take this pair, and this is a connected snake. So specifically for each P, I have this inequality satisfied. And why do I want to do that? Oh, sorry, let's just give you an example to start off. So in n equals to 5, I can take S prime and S like this. I collect the first intervals, then the second intervals, then the third intervals. I have all these pairs. And then I look at each one of those pairs and see if this is a connected snake, meaning if they overlap in a particular way and they are connected. And they have all intersections, and 4 minus 0 equals to 4, which is less than 6. And there you can check that this is a cover. So I want to define this cover because then it makes sense, let's find these properties, makes sense to define intersections and unions of S and S primes, which is just like fixing all the i's and swapping the j's in each position, right? In the example, for instance, so the intersection is just 2, 2, 3, 3, and 5, 6, and the union is given by 0, 4, 1, 7, 2, 8. Okay, so in general, we can, given any boot segment like this, we can define this, and for P and L in this range, we can define this element, which is just looking at the elements of S from the Pth position to the Lth position of the original thing, right? And in particular, when I consider, if I'm given a connected snake S, I can chop off the first element and the last element. Take two copies of them. One copy I chop off the first one, the second copy I chop off the last one. And the Mook-Young extended system is given by the following. So in the Grothendieck ring, we have this identity. So we have this module, or the tensor product, the associated modules is isomorphic to this, plus we have some new module showing up here, which is given exactly by the intersections and then the unions of the associated cover here. I'll give one example in a second. So this is just some motivation from the T-systems. Well, T-systems in general are not going to hold, like such equations. I mean, length 2 is asking too much in general to hold. But we could try to understand what the SOCO is. And here, in this case, we have that the SOCO of this tensor product is exactly V omega 1 tensor V omega 2, which is simple. And it's okay because this is a snake module is real, and we know by now that SOCO of this tensor product has to be simple. And we can completely compute the SOCO in this case. But this is a very restricted case, right? So we start with one snake and chop off just one element and another element. So it's very restricted. Well, just some words. I mean, it's extended desistance because the original desistance, they are the same kind of equations when we impose that the snake you started off is actually a curl over sticking. Right? Okay, so what I want to do is try to generalize these ideas of intersections and unions. But for that, I need a p-covering. And p-covering is essentially, again, I'm taking S and S prime to be snakes, okay? And I will say that S is a p-covering of S prime. If S is a covering of S prime in the usual way. And what I have to do here, for instance, is, so I take this P and I chop off, this is S prime, and this is S. Let's say I chop off the first P elements of S prime. I chop off the last two elements of S. Everything that remains from S has to cover what remains from S prime. Okay? I mean, this is some notation for this simple feature. It's not hard to see that if we have a P covering, we have actually a K covering for all K less than or equal to P. So just an example with working with the previous S prime and S, we have already proved that S is a covering of S prime. Now I want to prove that this is a one covering. So I drop the first element of S prime and I drop the last element of S. I end up with this. And then I check that this element covers this one, and it does, so it's a one covering. But it's not a two cover because if I drop these two elements of S prime and the last two elements of S, I end up with 2, 6, and 2, 4, and this is not connected snake anymore. So similar to what we defined as intersections and unions, I can define P intersections and P unions because once I have a P covering, so this makes sense. So I just look at the part that it's covered and forget the rest. And similar for the union. And associated to now a P covering, I want to define this element P pi as follows. So everything that I had dropped off, I consider the same associated polynomial. That's what I'm having as omega S 0 P. What I chop off from S, S prime, omega S. This is P R minus P. And what I obtain from this part that's a covering is the intersection and the union. So I take the product of all those four elements, and that's how I define this P pi. Again, same example. We have already been through all that. The S1 intersection. The one intersection is given by 2, 3 and 3, 3, 6, and the union is given by 1, 4, 2, 7, and pi 1 is just given by like that. So I just have this 0, 2 that I dropped off. I take intersections and unions, and this 5, 8 that I dropped off. Okay. So now we have all the notation needed to go to try to check the conditions we started off. The first condition, so let's try to approach the first condition, but in fact, I have a stronger result, which is using all those nice properties of snake modules. Suppose that S and S prime are snakes and that S is a P covering of S prime. Then there exists a chain of highest L weight modules, M0, M1, MP, inside the tensor product of those two snakes, such that the SOCO is exactly this first element. In fact, the highest L weight of each one of those modules is given by P chi, as I defined. And we know that the SOCO has to be reducible, so, and this M naught is the SOCO, so it has to be pi naught. We went away from this very restricted scenario of the extended systems to a generic setting where we only have these conditions being satisfied. In particular, and moreover, actually, we are able to prove that when P is bigger than or equal to 1, we have a short exact sequence like this. So what we're proving is if S is a 1 covariant of S prime, then M1 satisfies the condition I1. So remember that we needed some particular module, submodule of the tensor product, which has length 2, and M1 is that chi. Okay, as for condition 2, I just recall what we have to prove. So suppose that S1 is a 1 covering of S prime. Then we have to prove that that phi of M1 tensor M1 is non-zero for some particular special element omega. Recall that we have this surjective. Here we used to have the head of V omega S prime tensor V omega S, but this is exactly V pi, as we know now. I take the image of M1 tensor M1 in there. And since V pi naught is a submodule of M1, it implies that this particular weight space inside M1 is at least 1. And when we go at the tensor product, these weight spaces are well behaved with respect to multiplication. So this dimension is at least 1 again. On the other hand, here comes the important part from working with snake modules. We are able to prove that this same weight space has dimension 1 in this tensor product, and the squared of this weight has dimension 1 in this fourfold tensor product. Okay? And also in this module, which is the target. Well, since phi is surjective, it's mapping this particular one-dimensional space, which happens in here, to this only one-dimensional space that maps here. So this gives a non-zero module. And therefore, it has a reducible quotient, V omega. And now, with all this in hand, it's not easy really to show that this particular L weight is not an L weight of the target, hence cannot be an L weight of the image of M1, M1. So therefore, this omega has to be not equal to pi1 squared. And condition 2 is satisfied, as long as we have a 1 covering. Now we come to the difficult part, because at this point, V pi1 is our favorite candidate to be the imaginary module, and we are left to check that condition 3 is satisfied. Up to this moment, we have that this composition map is non-zero, and we have to check that this is 0. That's condition 3. Well, usually this is difficult, because we don't have an explicit description of omega. This is obtained all indirectly. And both V pi naught and V pi1 are not snake modules. So we don't have many tools to compute weights and Q characters and so forth. So this is very abstract at this point. However, there's one way out, which is, well, this module is generated by the lowest tensor, the highest. So I know for sure that a particular L weight has to be, which generates this module, has to be in this V omega. And this particular L weight is this. I mean, it doesn't matter about notation. We know there must exist some particular weight living there. So it suffices to prove that this particular L weight space cannot live in these submodules that I'm looking at. Okay, so it's some weight arguments, but in this loop version of things, but it's all very canonical in some sense. Again, not so easy because we don't have much control over these modules. However, there is a weaker way out, where instead of proving that this weight space does not belong here, I try to impose conditions on my initial data S and S prime in order to prove that the same weight space does not belong to a larger module, which are the Weil modules associated to each one of those dreamfield polynomials. I didn't say what Weil modules are, but you can think of the tensor product of every fundamental involved in the way in how I write pi1 and pi naught. So this module is a quotient. I mean, actually, this module here is a quotient of this. So if I prove that this particular L-weight space does not belong here, it certainly does not belong here, and then I get my condition. But I have to impose restrictions here. And the restrictions are exactly as follows. So the J1 prime has to be strictly less than I2, and J2 minus I1 prime has to be bigger than n plus 1. So once I impose the restrictions, this condition holds, which forces double dagger to hold and proves condition 3. And so in that case, if pi 1, under all these conditions, if we have that pi 1 is imaginary. And this is the main result, essentially. Okay, this condition seems to be a little bit artificial, and in fact it is, because that's the condition you have to impose so we could prove something. But it's not so arbitrary in the sense that I'm going to talk in a second. I forgot this example. So the same example I had all along. So we have already proved that S is a one covering of S prime. I only need to check this 2-star condition. So J1 prime for me is 0, is 2. I2 is 3, so it satisfies the condition. J2 is 7. I1 prime is 0, so 7 minus 0 is bigger than the rank plus 1. So we are safe, and so this module V pi 1 is imaginary for n equals to 5. But in fact, it remains imaginary for all larger rank. We can prove that. So that's why this condition seems a little bit artificial. I'm not stating the full strength of the theorem, but this is the easy version of that. Okay, so a couple of remarks. Why that restriction is not so arbitrary. If I start with a snake S, there is a canonical way to define another snake S prime, which is some sort of dual of the snake. And it's not some sort, it's actually the dual, because when I take the dual module of V omega S prime, this is exactly V omega S. In that particular case, V pi naught is C. And in all those cases, we are able to prove that this 2-star condition holds. This extra weird condition holds. So as long as we have a one covering of snakes, and S prime is of this form, pi 1 is imaginary. So basically, if you start with any snake, you take this dual. There are some conditions for this dual to be for this to be a one covering, but you always get an imaginary module. And this is exactly what we did with Chari when we first started all this, by taking S not being a generic snake, but a particular snake where each interval has the same length, and the S prime is given by this dual procedure here. One twist in the story is that actually in that paper, we used similar methods to produce infinitely families for types A2 and D4. So all I talked about here was A4, type A. There we proved D4. And one thing that I did not mention is that this one covering implies the rank to be at least 3. So by this procedure, exactly like this, we cannot produce imaginary types in A2, imaginary modules in A2, but here we're able to do by some different methods. Similar, but different, okay? I mean, the nice part is because these examples in general, they do not fit the framework of Lapide and Minguez, because for that you'd have to look at the concatenation of the segments, and this would have to be regular, and in general for us it's not regular. So this runs away of their restriction. So this I mentioned before. So this is the original Leclerc's example. He was able to prove that V pi 1 for this pi 1 is imaginary in type A4. But in fact, using our methods, we can prove in type A3 this is still imaginary. So he had to do A4 because of these conditions of the Schur-Weil functor. So that's where he could guarantee something. So, and therefore, for this example, we have to recover by taking S and S prime like this. So this is dual, and this was also covered by this work with Vyjayanthi before. And in this very particular case, we have that V pi 1 tensor V pi 1 is isomorphic actually to the direct sum of these two components. So this is not in the composable module. which is also surprising, but we have no idea how to prove this, if this always happens, or if there's anything that you can split off the tensor product of imaginary modules. Okay, some other remarks, since I still have a little bit of time. Again, this weird condition that we have to throw in is not always needed. For instance, when r equals to 2, when it takes snakes of length at 2 exactly, we can prove this in general. So this can be translated as follows. So if you just start with some snake of length 4, with this kind of restrictions just to make sure that I3, J3, I4, J4, 1 covers I1, J1, I2, J2, you always get an imaginary module with this weight. If S and S prime are not of Krea type, they are Kirlover-Sticky modules, again, we can prove that the associated pi1 is imaginary. We don't have to look at that extra condition for that. And one final remark, which I think it's interesting at least, is that, so suppose, okay, we have all these and you can produce this pi1 from a E1 covering. We are able to construct actually 2 new snakes, S tilde prime and S tilde, in a way that S tilde covers, just covers, not one cover, S tilde prime. And this pi1 that I started off from this original S's is the product of intersections and unions. So this is telling us that this pi1 can be seen as this, not this term above the socle, but the socle itself of some other tensor product. So in the case where we have proved that this pi1 is imaginary, we proved also that some tensor product of snake modules could be imaginary, which I don't think there was, I haven't heard of before. So just continue that example. I have the same pi1 here that we are used to. We can always find some A and B's here. Here, there's no choice. A has to be 1, B has to be 7, but it's just for exposition, the kind of bounds they have to satisfy. And I define the S tildes and S tilde primes like this, and I get this condition. So pi1 is exactly the intersection and the union of the corresponding element. And that's all. Thank you. They are prime snake modules. So let's look at the prime ones only. Prime snake modules, definitely, they come from cluster mutations. So that's why they are reachable. But they do not, in general, they are not part of this initial seed or anything like that. So if you remember, last week, Hernandez told us that we have to start with Kirlover-Sticky modules for the initial seed, but what those people proved, when it's reachable, they exhibit some infinite sequence of mutations in that original seed to reach such modules in every time. So that's what I know. That's how it at least connects with the cluster theory as far as I know.
I think the condition you mentioned as double star, that only shows up to show that the weight is not in the tensor of the standard modules, right?
Yes, exactly.
So, and with these extra cases, you use the same approach, that it's not a weight, or? So you mentioned a few extra cases.
Yeah, the extra, that's true. So the second condition is just to guarantee that this weight space is not a weight of the standard module here. That's true.
Yeah,
so but in general, this is not true. This fails to hold. Mm-hmm. Even for known cases where pi1 is imaginary, this fails to hold in general. Okay? Right. So what we do in these extra cases, well, when r equals to 2, this is too small, so we can control it easily. So this is essentially done by hand in some sense. And the case when we are working inside Kirlover-Sticky modules, then we have extra control, because when everything some sort happens inside that tensor product of snake modules, mm-hmm. and Kirlover-Sticky modules are the most rigid things you can have. In some sense.
And nothing, no chance to go in between these two modules to get a weaker condition? Or?
I mean, I tried, but I mean, yeah, I couldn't. I failed. So, I mean, well, the conjecture, of course, is that regardless that condition double star, pi1 is always imaginary. So this is the most natural conjecture to have, and I think it's true. I just have no ways to attack it, at least with these methods.
Thank you.